So here we're going to do another example related to the hydrogen atom. In this example, we're looking at what is the average radius, which you'd find the electron from the hydrogen atom, right? The average radius is related to solving this expectation value of r, right? Which is the integral of psi star r psi, and then r squared d r sine theta d phi, right? So that is the integral we're trying to solve, okay? Right, and note here, right, the expectation value of something, right, is the wave function times that thing times the wave function, right? Then we have, you know, the dx, dy, dz thing here, right? But for polar coordinates, it's r squared sine theta dr d theta d phi, right? The other note here is that if our wave function just depends on r, which this does, right, then this integral simplifies down to just 4 pi times the integral of our radial part of our wave function, you know, squared, should put that there, right? Or just, I guess, f, right? F and r, right? So radial part of the wave function times r squared dr, okay? So basically, right, the theta and phi parts simplify out and just give us a factor of 4 pi, okay? You know, if we're ever needing to do something like this, really what this simplifies down to is an integral over theta times an integral over phi times an integral over r. You just do each of those one-dimensional integrals independently of each other and multiply the final values together. Okay. So we know in this problem that r here is equal to square root of 1 over pi times 1 over a naught to the 3/2 power, right? Times e to the minus r over a naught, okay? Right, and so we know that is our wave function, right? And so, yeah, I'm just verifying that is in fact the wave function, right? So that's our wave function, okay? So plugging in for then the integral that we have, right? We're trying to, right, we have 4 pi times the integral from 0 to infinity, because that's the values that r can take, of r times r times r, r squared, the star there, right, dr, right? This is what we're trying to solve. And my apologies for my handwriting. This capital R star, little r, capital R, r squared, okay? So this then is equal to 4 pi times the integral of 0 to infinity of, right, so plugging in for what r is here, we're going to have an r cubed hanging out in front, and then we're going to get 1 over pi times 1 over a naught cubed times e to the minus 2r over a naught, okay? And then dr, right? So again, r cubed here because we just got r squared times r, and then we get pi because we have square root of pi squared. We get, you know, 1 over a naught because we get, you know, that squared, and then e to the minus r over a naught times e to the minus r over a naught is just e to the minus 2r over a naught, right? So this then is equal to 4 pi, right? And then we can look up, then pulling out the other constants, right? We get 1 over pi, right? Let's erase this here. Try this again. All right. If we can get a better job writing this out. Okay. So we get 4 pi, right, times 1 over pi times 1 over a naught cubed, right, times the integral from 0 to infinity of r cubed e to the minus 2r over a naught dr. Okay. This then simplifies using that integral that was given at the beginning of the problem, right, of 4 over a naught cubed, okay, and then times 3 factorial over 2 over a naught to the fourth. Okay, and so that then simplifies down more. So that's going to be 4 times 6, right, divided by a naught cubed, right, and then 2 to the fourth power is 16. So that's 16 divided by a naught to the fourth. So this simplifies down here. So we get 24, right? So you have a naught to the fourth and a naught cubed. Those are kind of simplifying, canceling with each other to get a factor of a naught on top. And then this is 16 on bottom, okay? And then that simplifies down to just 3 over 2 a naught, okay? And so this is our average radial distance, right? 3/2 a naught, okay? A naught is the Bohr radius. It's what, like 0.5 angstroms? So this is something like 1.5 angstroms away from the nucleus, right? Which an angstrom, for those who don't know, is 1 times 10 to the minus 10 meters. Okay, so this is like 1.5 times 10 to the minus 10 meters away from the nucleus. It's kind of the average distance the electron is from the nucleus in the ground state of the hydrogen atom. Okay. All right. So the next example here is we're calculating the average potential energy of the hydrogen atom in, again, that ground state wave function, right, and the average kinetic energy. Okay. So again, we're going to use kind of the hints here to simplify the integral over polar coordinates, right, to just simple integral over r. Okay. And so we're going to kind of use what we'd done last time, right? Right. So the average potential energy, right? Well, the potential energy, right, is for the hydrogen atom is equal to the coulombic attraction between the electron and the nucleus, okay, which ends up being minus e squared over 4 pi epsilon naught r, okay, which a lot of those things are just constants, so this is just minus e squared over 4 pi epsilon naught times the average value of 1 over r, okay. And so that's what we're trying to solve. We're trying to solve for the average value of 1 over r, right, to get the average potential energy, okay. So to solve that, we have to solve the integral, right. So average value of 1 over r is equal to 4 pi times the integral of 0 to infinity of r, the radial wave function, star 1 over r squared dr, okay? Which, right, this simplifies down to 4 pi, integral of 0 to infinity, the radial wave function, right, plugging in, you can look in the previous slides or things like that, look it up, right, plugging in is 1 over pi, right, times 1 over a naught cubed, okay, and then r squared divided by r, just because it's a factor of r, and then this is e to the minus 2r over a naught dr, okay. So this gives us kind of the integral we need to solve, so simplifying this again, 1 over r is, okay, pi's cancel, so I'm left with 4 over a naught cubed, okay, times the integral of 0 to infinity of r e to the minus 2r over a naught dr, okay, which this then, using the integral table that we have, right, this then simplifies down to 4 over a naught cubed times what the integral is equal to, so that's 1, so it's 1 factorial over 2 over a naught squared, okay? Which this then simplifies down, so 2 squared is 4, so the 4's cancel, and this simplifies down to 1 over a naught, just 1 over a naught, okay? So that's what 1 over r is. So the average potential energy is then equal to negative e squared over 4 pi epsilon naught times 1 over a naught, okay? And so, right, if you then plug in for what a naught is, okay, which is a bunch of junk, right, that you know we can look up on the previous slides or such. It's a factor of h bars and blah blah blah. That this simplifies down then to negative mass of the electron times charge of the electron to the 4th power over 4h squared epsilon naught squared. Okay, right. And so this gives us the average potential energy for the electron. Okay, and so now the question is what is the average kinetic energy? That's the second part of the question, right? So the next part is trying to find the average kinetic energy, right? Well, that's a little trickier if we try to solve the integral, because solving that integral, right, the kinetic energy, right, is related to solving 1 over h squared over 2m, and then it's going to be something like r d dr plus d squared dr squared, or something like that. Something like derivative with respect to r, stuff like that. We're going to take derivative of our wave function and blah, blah, blah. It is a complicated mess that we don't really want to solve, right? But we know for the hydrogen atom, right, that, well, for any system, right, our total energy, right, is just equal to potential energy plus kinetic energy, right? Just simple Newtonian mechanics, right? Total energy is just potential plus kinetic, right? Well, we just solved for the potential energy, okay? And we know the total energy for the hydrogen atom in the 1s orbital, because n equals 1, z equals 1 for the hydrogen atom, right? So we know for the hydrogen atom, right, that the total energy is just equal to 1 over, what is it going to be? 8, let's see here. Sorry, I'm going to look this up. Right, we know this by looking it up. We don't know this off the top of our heads, right? So looking that up, the total energy for the hydrogen atom is the mass of the electron times the electric charge, so 4th power, all over 8 epsilon naught squared times h squared times n squared, which is just equal to 1. Okay, so let's just delete that 1 there, right? And so that is the total energy, right? We found the average potential energy, which was m e mass of the electron, e to the 4th, right, over 8. So it's negative 8. Oh, not 8, sorry. Jeez. Right. While recording these things, I can't really go back to the previous slide to see what the value was, right? It was 4 h squared times epsilon naught squared, okay? And this plus average kinetic energy, right? And so, and there should be a minus sign here, right? So if you add this onto the other side, what you'll see is the average kinetic energy is the exact same thing as the average potential energy, which is the mass of the electron times the electric charge to the fourth over 4, should be a minus sign here, over 4h squared epsilon naught squared, okay? So the average kinetic energy in the ground state for the hydrogen atom is the same as the average potential energy, which is just 1/2 the total energy. Okay? Now this isn't necessarily true for all states, right? All orbitals and things like that for the hydrogen atom, but it is true at least for the ground state. Okay?